Chapter 10 discusses hypothesis testing, which kind of like you probably think about a hypothesis in science class, yes, where you make a claim and then you do the science fair project and you decide if your hypothesis was correct or not. Yes? Sounds familiar? So that's going to kind of be what we're doing, but there's specific language and statistics that we're going to use to discuss these different hypotheses. So let's just see, example 1 just jumps us into the idea of why we have hypothesis testing in the first place. A friend of yours wants to play a simple coin flipping game. If you flip the coin, right? He says that if it comes up heads, I win. If it comes up tails, your friend wins. We flip the coin 5 times, and we get tails, 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 tails. Is your friend cheating? Let's mathematically figure this out. So let's throw back to chapter 5. What is the probability of getting tails, 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 tails? We break that down by the independence of these different events. What is the probability of getting tails once? 50-50, so we're going to use the number 1/2 because you have half of a chance. And then since these are all happening independently, we multiply them together. So what's the probability of getting a second tails? Another half. How about the third one being tails? Okay. And then the fourth one being tails. And then so it's 1/2 to the 5th power. 1/2 to the 5th power, if we compute that, is 0.03125. So mathematically, we can evaluate if our friend is actually cheating in this game. So if that's the probability of getting 5 tails in a row, is that considered unusual? Is this? Yeah, it's less than 5%, less than 0.05. So this is considered unusual. I'm going to write down that 3% is definitely unusual. So either one of two things is happening. Number 1, either your friend is using an unfair coin that is like weighted differently, which means they're cheating, or they're just, option 2, extremely lucky. Because there is a possibility of this happening. So before we ran this experiment to decide if our friend was cheating, we probably think to ourselves, we're going to say he's cheating if it's unusual, if it's less than 5%. We've set this hypothesis, and then we saw the game, and then we can draw a conclusion on whether what we got out of the data means that we accept or we reject our hypothesis. This is the heart of hypothesis testing. So we make an assumption about reality and then gather data to determine if it contradicts our assumption. But we're going to use very specific language as we're doing it. So again, today's a big writing day. Today, what we're going to work about, and the way hypothesis testing in statistics is we do have to set a hypothesis. Hypothesis is a statement regarding a characteristic of one or more populations. So we could say we think the standard deviation of people who, whatever the characteristic is, or we think the sample mean, blah, blah, blah. We think the population proportion is blah, blah, blah. We're setting a hypothesis. Hypothesis testing is the procedure that we use that we're going to discuss today based on sample evidence and probability that we use to test these statements. So in general, in science and in statistics, we would have started before we even collected our evidence back in chapter 1. We would have started by making a statement regarding the nature of the population. That's what we're doing now. Once we have that statement, we go out, we gather our data to test that statement. We bring it back, we go through chapters 3 through whatever to analyze the data, and now we can come back to chapter 10 to assess the probability of the statement. Because we use sample data to test hypotheses, we cannot state with 100% certainty that the statement is true. Instead, we can only determine whether the sample data support the statement or not. We're not choosing if something is proven true. We're saying it's proven supported by the data. Because the statement can be true or can be either true or false. So it is or it isn't larger than something. Hypothesis testing is based on 2 types of hypotheses. The null hypothesis, which we denote as H naught, I know that's a subscript of 0. Oh, no. But it is read as H naught. H naught is our statement to be tested that is of no change, no effect, and no difference. It is the status quo. It is assumed true until evidence indicates otherwise. That's H naught. The alternative hypothesis, H1, is the statement we are trying to find evidence to support. This is the one that is some sort of change from the status quo. The null hypothesis is, like I said, a statement of status quo or no difference and always contains a statement of equality. So our null hypothesis will say that something is equal to something. The null hypothesis is assumed to be true until we have evidence to the contrary. We seek evidence that supports the statements from that alternative hypothesis, H1. There are 3 ways to set up the null and alternative hypotheses. The first one is called a two-tailed test. We're basically saying that the hypothesis of equality, your H naught, will just be tested against some parameter not being equal to that value. So we would say H naught mu equal to 5. H1 mu not equal to 5. Just basically trying to prove that it's not one particular number. That is called a two-tailed test. A left-tailed test is when you check if something is actually less than your hypothesis, your null hypothesis. So H sub 0, oh my gosh, I just taught sequences in my class before this. H naught is, let's say it's mu equal to 7. H1 would be mu less than 7. It's called a left-tailed test. Easy to remember this because what direction is this little arrow pointing if this was an arrow? Left. Left-tailed test. Left, less than. Your right-tailed test is your greater than hypothesis. So we could say that H naught is equal to maybe P equal to 145 and H1 is P greater than 145. But the number should be the same value each time. The statement we are trying to gather evidence for, which is dictated by the researcher, again, before any data are collected, determines the structure of our alternative hypotheses, whether we're doing a two-tailed, right-tailed, or left-tailed. One of the main things we're doing today is being able to write these hypothesis statements. So on the back page, we have 3 examples of this happening. For each time you structure these hypotheses, you're going to identify the parameter to be tested. Maybe it's mu, maybe it's p, maybe it's sigma. You're going to determine the status quo value. That gives you the null hypothesis. That is the status quo. Then you're going to determine the statement that reflects what we are trying to gather evidence for. That becomes your alternative hypotheses. For most of these, I wrote out a lot of the words for you so you could see that every time we do this, we're putting it in context of the problem if you're asked to write these things in words. But we will also give the hypothesis in terms of symbols, mathematical symbols, so that we can do both. Letter A says, the Medco pharmaceutical company has just developed a new antibiotic for children. 2% of children taking competing antibiotics experience headaches as a side effect. A researcher for the FDA wishes to know if the percentage of children taking the new antibiotic who experience headaches as a side effect is more than 2%. What was the status quo? 2% of children who take an antibiotic medication have a headache as a side effect. So this 2% right here is the, wrong color, is the status quo. So our H naught in words is the proportion of individuals taking the new drugs who experience a headache as a side effect is 0.02. That was what was happening before we introduced the new antibiotic. That's the status quo. Symbolically, we would use P for proportion and we would say H naught is P equal to 0.02. Because that's population or proportion equal to 0.02. What we are trying to test is what? Read it specifically again. Read the last sentence of that blurb.
More than 2%.
We want to know if the people who take the new antibiotic would be more than 2% having headaches. So our H1 is the proportion of individuals taking the new drugs who experience a headache as a side effect is more than 2%. It sounds like we're just rewriting the same things, and we are. Part of hypothesis testing is correctly and fluently writing these hypotheses. Now, H1 here, since we want to know more than, we would literally just use the more than symbol to show that we are just trying to compare if the status quo or if more than is happening. Since we used more than, is this a two-tailed, left-tailed, or right-tailed?
Right-tailed.
This is right-tailed. Very good. So yes, if we're writing the hypotheses out in words, you are expected to basically repeat what the study is studying, because we have to make sure we are completely telling the researcher, the person reading our article, all of these things, exactly what we're researching and what we're looking for. Part B says the Blue Book price of a used 3-year-old Chevy Corvette Z06? Okay, Z06, I don't know cars, is $59,083. Grant, this guy, wonders if the mean price of a 3-year-old Chevy Corvette Z06 in the Miami metropolitan area is different from $59,083. Okay, what is the status quo? The price of the Corvette from Kelley Blue Book, right? So this right here is our status quo, which means our H naught is the sentence. The mean price of a 3-year-old Corvette Z06 in Miami is no different from the Blue Book price of $59,083, because there's no difference between them. Now this time we're just studying the mean. So instead of P, when I use symbols, what symbol am I going to use? Mu, because mu is the mean. So we're going to say mu is equal to $59,083. What are we trying to study here? What are we trying to prove? That it's different from the status quo. So the mean price of a 3-year-old Corvette Z06 in Miami is different from the Blue Book price that we started with, that is our status quo, $59,083. How would we write this one in symbols? Mu does not equal $59,083. If we're just trying to see if it's different from the status quo, is that a two-tailed, left-tailed, or right-tailed? Two-tailed hypotheses. Part C, the standard deviation of the contents in a 64-ounce bottle of detergent is using an old filling machine is 0.23 ounces. Whatever. The manufacturer wants to know if a new filling machine has less variability. So what is the status quo? What normally happens? The standard deviation amount in the bottles is, ooh, that's the size of the bottle. Standard deviation, 0.23. That is what normally happens. So we want to see if the standard deviation amount in bottles is no different. And we have to put the word from the old machine, which is 0.23 ounces. So our H naught, remember, is no change, no difference. It is our status quo. What symbol do we use for standard deviation? Sigma. So sigma would be equal to 0.23. What are we trying to study or measure here? Less variability. Now, remember, standard deviation is our measure of variation. right? It's our measure of spread. So the standard deviation amount in the bottles, we're looking to see if it is less than the old machine, which is 0.23 ounces. So our H1 in symbols would be sigma less than 0.23. Since we used less than, is that two-tailed, left-tailed, or right-tailed? Left-tailed. Less than, left-tailed. It does require you to write these statements and write them in words for what we're studying. The null hypothesis is what will not change from the status quo, no difference. H1 is what we're trying to see. Now, of course, when we run studies, there's always a chance that we make a mistake. So when we're testing a hypothesis, there is always a possibility that our conclusion will be wrong. So to make matters worse, you won't know whether you're wrong or not. But don't fret. We have tools to help us manage these incorrect conclusions. There are 4 outcomes from hypothesis testing. The first outcome, is that we reject the null hypothesis when the alternative hypothesis is true. That's good. We want that. That is correct. We reject the status quo because in reality, the alternative hypothesis is true. Second option is that we do not reject the null hypothesis when the null hypothesis is true. This decision would also be correct. However, there are 2 types of errors we can make when it comes to hypothesis testing. The first one is that we reject the null hypothesis when the null hypothesis is true. This decision would be incorrect, and this type of error is called a type 1 error. The other error, another option, is that we do not reject the null hypothesis when the alternative hypothesis is true. This decision is known as a type 2 error. This is hard to keep track of. There's many things we can do to keep track of the types of errors, but if you look at this nice visual situation we have going on here, you'll see that both of the correct decisions occur when we have lined up what is true and what we have not rejected. If we do not reject H naught and H naught is true, that's correct. If we reject H naught and H1 is true, that's a correct decision. However, if we reject H naught, when in reality H naught is the thing that's true, that's called a type 1 error. And if we do not reject H naught, when in reality H1 is true, that's called a type 2 error. And that still doesn't really help kind of distinguish between the 2 types of errors. But if you think about this like a courtroom, these sorts of errors actually make a lot of sense. Let's think about a criminal trial. In any trial, the defendant is assumed to be innocent. We give the defendant the benefit of the doubt. The district attorney must collect and present evidence proving that the defendant is guilty beyond all reasonable doubt. Because we are seeking evidence for guilt becomes the alternative hypothesis. Innocence is assumed. It is the status quo. That means that innocence is the null hypothesis. So if we look here, if we look at our study, H naught would be the defendant is innocent. H1 would be the defendant is guilty. Those are our 2 hypotheses. This would be a 2-tailed hypothesis. So in a trial, the jury obtains information, then deliberates about the evidence, and it either convicts the defendant or declares the defendant not guilty. Okay, right? So we reject the null hypothesis. The defendant is guilty. Or we declare the defendant not guilty. Here's something very important when it comes to hypothesis testing. Notice that we never say the defendant is innocent. They say not guilty, right? The null hypothesis is never declared to be true. The 2 correct decisions are either to declare I want to stick on that idea for a second. The null hypothesis is never declared true. We'll just say not guilty. Not innocent. We didn't say that. We said not guilty. That's the same thing with these kinds of hypothesis testing. Not saying necessarily that the null hypothesis is true. It's just that we don't have enough evidence to prove it otherwise. The two correct decisions are to declare an innocent person not guilty or to declare a guilty person to be guilty. So let's look at our table up here. The first correct decision is to declare that an innocent person, do not reject innocence, is actually innocent. That's correct. Or we reject that they are innocent, being that they are guilty. That's a correct decision. The errors come in when we make mistakes here. A type 1 error is like putting an innocent person in jail. A type 1 error. We rejected that they are innocent, even though they are. We've put an innocent person in jail. That's a type 1 error. A type 2 error is like letting a guilty person go free. So we did not reject H naught. We did not reject that they are innocent, when in fact, they are actually guilty. So it's the easiest way in theory to remember the difference between type 1 and type 2 errors. Let's see if we can think about the type 1 and type 2 errors in context of our headache example from earlier. So it's the same information. The Medco pharmaceutical company has just developed a new antibiotic. 2% of children taking competing antibiotics experience headaches as a side effect. A researcher for the FDA wishes to know if the percentage of children taking the new antibiotic who experience a headache as a side effect is more than 2%. So we conduct this hypothesis testing. We have H naught being P equal to 2%, and H1 being P greater than 2%. So more than. What would it mean for us to make a type 1 error in this scenario? A type 1 error, remember, is that we reject H naught when H naught is true. So we would say, this is a writing situation, we say that the proportion of children who have headaches after taking this is 0.02. That is us rejecting H naught, because H naught was that it's equal to. But we say that it's more when, in fact, the proportion of children who experience a headache is not greater than 2%. So we've made a mistake. This is a type 1 error. Rejecting the status quo when the status quo is actually true. So what would it mean for us to make a type 2 error? In a type 2 error, do we reject or do we not reject H naught? We do not reject H naught when in fact H1 is true. So we put that in context of this problem. We would say that the proportion is equal to 0.02, which means we do not reject H naught. Notice I did not say we accept H naught. I said we do not reject it. That's the difference. We say that P equal to 2%, aka do not reject H naught, when in fact the proportion of children who get these headaches is actually greater than 2%. These are our two types of errors. Make a commitment right now to try to make sure you understand the difference between the two errors. When we studied confidence intervals in the last chapter, we learned that we never know exactly whether a confidence interval contains the unknown parameter. So similarly, We never know whether the conclusion of a hypothesis test is correct. However, just as we place a level of confidence in the structure, in the construction of a confidence interval, we can assign probabilities making type 1 or type 2 errors when we are testing hypotheses. So alpha is now used as the probability of making a type 1 error, which remember is rejecting H naught when H naught is true. New Greek letter for you, beta is going to represent the probability of making a type 2 error, the probability of not rejecting H naught when H1 in fact is true. We need these alpha and these beta numbers. This creates what's called a level of significance. Alpha is called the level of significance, which remember is the type 1 error probability. This is chosen by the researcher before sample data are collected. This is something we choose when we do these studies. The choice of the level of significance depends on the consequences of making a type 1 error. If the consequences are severe if we mess this up, the level of significance should be very small, say 1%. However, if the consequences are not severe, a higher level of significance can be chosen. But the reason we have to choose these is because alpha and beta are inversely related. The probability of as the probability of a type 1 error increases, the probability of a type 2 error decreases and vice versa. So if we allow ourselves to have a very slim window of a type 1 error, we are more likely to have a type 2 error and vice versa, which again depends on the consequences of what happens if we accidentally get it wrong. For example, in our court analogy, a jury is instructed that the prosecution must provide proof of guilt beyond all reasonable doubt. This implies that we are choosing to make alpha, the probability of making a type 1 error, putting an innocent man in jail, small so that the probability of convicting an innocent person is very small. The consequences of the small alpha, however, is a large beta, which means many guilty defendants will go free. So there's a cost balance to alpha and beta. And we choose this before we start our studies in general. But once we have discussed type 1, type 2 errors, we've looked at the sort of things that can happen. We've chosen our level of significance. We've run our study, all of that stuff. We have to be able to write conclusions to these hypothesis tests. Again, more writing. It is important to recognize that we never accept the null hypothesis. Notice, I never said accept H naught. I said reject or do not reject. That's significant that you use the correct language there. Again, the court system analogy helps us to illustrate the idea. If the null hypothesis is innocent, then when the evidence is presented to the jury and it's not enough to convict beyond all reasonable doubt, the jury's verdict is not guilty. They don't say innocent, they say not guilty. So they're rejecting or not rejecting H naught. Notice the verdict does not state that the null hypothesis of innocence is true. It states that there is not enough evidence to conclude guilt. So the sample evidence can never prove the null hypothesis to be true. By not rejecting the null hypothesis, we're saying there's not enough evidence to reject our assumption that the null hypothesis is true. So we need to write conclusion statements that say that. It's going to sound like we're repeating ourselves, but again, in the language of statistics, it's good to be extremely clear in what you're saying. So using our situation from example 3, which is the headache study, where H naught is 2% of the population would have headaches, and H1 is more than 2% would have headaches, we're going to state the conclusions with the assumption that the sample evidence indicates the following. Number 1, part A, we're going to say that the sample evidence indicates that our null hypothesis is rejected. We reject H naught, which means we're trying to find a way to say we reject this. We would say, and I've written part of it here for you, the statement in the alternative hypothesis is that the proportion of students taking the new antibiotic who experience a headache as a side effect is more than 0.02. because the null hypothesis, p equal to 2%, is rejected, there is sufficient evidence to conclude that the proportion of children who experience a headache as a side effect is, in fact, more than 2%. We're stating the conclusion with the assumption that this is happening. But let's say when we run our study, we actually do not want to reject the null hypothesis. How does that change our conclusion sentence? We would say, because the null hypothesis is not rejected, there is not sufficient evidence to say that the proportion of children who experience a headache as a side effect is H1, meaning is more than 2%. We're not saying that it exactly is 2%. We're just saying there is not sufficient evidence to reject H0. The language of these hypothesis testings and how you communicate statistics needs to be cleared up, because this is a huge deal when it comes to statistics, is communicating your findings appropriately and drawing the conclusions appropriately. Questions, comments, concerns?